We just covered eigenvalues and eigenfunctions. Now let's talk about Sturm Liouville. Well, here's the Sturm Liouville equation. Well, I don't know why it's put in this form or anything else yet. There's the Sturm Liouville equation. And if it comes with boundary conditions that look like this is called the Sturm Liouville problem. And there's an important theorem. Any Sturm Liouville problem will generate an orthogonal and complete set of eigenfunctions, where the weighting function of the orthogonality relationship is this P function P of X. And remember, when we covered orthogonal and complete sets of functions, we could expand any function using that set, that orthogonal set. We did that to derive the Fourier series. That was one orthogonal set. Well, it turns out any solution of this equation with these boundary conditions is also going to be an orthogonal set. So we can expand a function with this guy's eigenfunctions using, with the orthogonality relationship that has this P as a weighting function. So any such solution we can expand a function with that. So it doesn't just have to be the trigonometric Fourier series or the cosines and sines or the e to the I n pi p over x or whatever that was. There's all kinds of functions that we can use, orthogonal sets of functions. Couple of subtleties. Well, first off, if these are your boundary conditions, you can't have both the A and the B equal 0. At least one of them has to be non-zero. And there's little variations on these boundary conditions. If this R function at one of the endpoints of X, by the way, the endpoints of X are A and B. X goes from A to B here. If this R function is 0 at either end, instead of this kind of boundary condition, just that your solution must be bounded at that boundary. So if R at A is 0, your solution must be bounded at X equals. And one other set, it's called the periodic condition, these set of boundary conditions, where it's the function and its derivative are equal at both ends. So that's a Sturm Liouville problem, and it's the big theorem. It's a way to generate orthogonal and complete sets by which we can expand a function. And we're going to do that with a few things other than the good old Fourier series as you know it. That form you just saw is called the self-adjoint form. And we like to get it in that form because then this P, which is the weighting function of the orthogonal relationship, is apparent. We know the weighting function if we can get it into self-adjoint form. If we just go ahead and take this derivative here, this is the same equation. And we'll look at this in a minute. The Legendre equation has this form. And also, it can be proved, and I do in my lecture notes. By the way, I have complete lecture notes. If you ever want them, email me. I'll try to put my email address on this. That goes for any of the videos I make. If you want more materials or have questions, email me. But this is another form of the Sturm Liouville equation. It's equivalent to this. And you can get from here to the self-adjoint form using this. This basically is a recipe for how to go from this format to that format. And again, why do we want to do that? Because that makes the weighting function apparent. In this format, we don't know what the weighting function is. Yeah, this relates how the A, B, C, and D relate to the R, Q, and P. And we'll do an example of how to go from this form to that form in a little bit. Let's first look at this form then. Here's the Legendre equation. If this up front here, we call that R of X, and what's its derivative? What's the derivative of this R? Minus 2x, right? And that's what's there in the Legendre equation. So the Legendre equation is already in Sturm Liouville form, where n and n times n minus 1 plays the role of lambda. And you'll see that Q is 0 here, and P is 1. Might be hard to see. Here's what we're comparing to the Legendre equation. Q is 0. No Q. Lambda times y. Which means the P is 1. So the Legendre equation is a Sturm Liouville equation. The solution is valid only on this interval, remember? And the R at those endpoints, look at what R is. At plus and minus 1, R is 0. So at those boundaries, that's this little, that's this little exception right here. In this case, R at both boundaries is 0. So the condition, instead of these conditions, the boundary conditions become that the solution must be bounded at the two endpoints of the interval, at A and B. And remember, you got the Legendre equation had two solutions. The Legendre polynomials was one, then there was that second solution. It wasn't a polynomial, it was an infinite sum. But I will tell you that that second solution is not bounded at the endpoints. So we're going to reject those solutions and only use the Legendre polynomials, which are good as long as these n's are integers. That generates the eigenvalues. And the P was 1. So here's the orthogonality relationship. Remember, it's the, well, you multiply the two functions, actually multiply the function and the other function's complex conjugate, but these polynomials are real, so we just multiply them together, times the weighting function, which is 1 in this case, and then integrate it. In this case, we'll assume we're going to solve it for the whole interval of convergence. So those will give us the limits of this integral. So this is our orthogonality relationship. This goes back to when we talked about orthogonal expansions, which is several recordings ago. I'll do this example of a different kind of case in another recording. That's the introduction of Sturm Liouville and why it's important. And well, we'll just save the rest for next time.